Section 5.2, page 3. So remember, we're dealing with the definite integral. Example 4 reads, a professor walks along the whiteboard in front of the classroom as she lectures. The velocity, v of t, in feet per second of the professor t seconds after class has started is represented by the graph given. You can see it off to our right. Approximate, the displacement and the distance traveled by the professor 3 seconds after class starts by calculating R3. So we remember the R means that we're dealing with right endpoints. N equals 3. So we'll go into that, but I want to really quickly go back to displacement and distance traveled. This is a continuation of the previous video where we stated displacement essentially is the net area traveled, if you want to think of it that way, but it's the distance between the starting and ending point. I actually heard a joke once that said if you die in the hospital you were born in, your velocity is 0 because your whole life started and ended at the same point. Probably a tasteless joke. But the distance traveled is actually how much ground was covered. And so we need an absolute value to eliminate the net effect of subtracting off area that was, considered negative. We're not subtracting a negative, so I might not have worded that correctly. Excuse me. So going back to the question, we have R3. So we need to know the width of our rectangles. So because this is being measured 3 seconds after class has started, our range is from 0 to 3, and so the total time, the distance of time is 3 seconds. Split into 3 intervals means we have these 1 second intervals. So zooming in on our graph, if we had 0 seconds, 1 second, 2 second, and 3 second, which is where we stopped measuring time, I had drawn these dashed lines at all of our intervals. And then as we trace the curve amongst each column, I found the right side of the column and came across to find the height. My second column came to the right side of these two values and read across to get 1 second. And my last column, the right side, read across at -8 seconds. So we've got this information where I've taken this graph and kind of superimposed it off to the left. Now, if we're just talking distance traveled, the area that's been covered, then we have our first rectangle. Width 1, height of 4 gives us an area of 4. The middle rectangle is a width of 1, a height of 1, which gives us a total area of 1. And our last rectangle, because we're just looking at area, a width of 1, a height of 8 gives us a total area of 8, and therefore the total distance traveled, the sum of those numbers, is 13 feet. But when we're asked for the displacement, how has the total distance changed over time, that last rectangle needed to be negative because it was below the x-axis, as you can see to the left where I highlighted in the graph. So with subtraction, we get -3 feet. That might seem odd, but imagine it this way. Class starts here, the teacher walks 4 feet. They walk another foot, but then they walk 8 feet the opposite direction. So when class started here, there was a net of -3 feet from the original starting place. Next, let's discuss the midpoint rule. So now we've seen this formula where we actually had the word limit in front of the summation notation. Since it's removed, we're using approximate instead of equals. We've dealt with the midpoint rule already, where we know that we're going to have some width of each rectangle, the end point minus the starting point, divided by how many rectangles we want. And this gave us the width. And then basically what we would do is we would take that width and add delta x to get to the next column endpoint. But remember, we want the midpoint. So we're going to divide those two column start and end point values by 2 to get the middle. and therefore we're really using these for our x values. I make a note here that if you recognize this bar on top, that think of that as average, right? If you remember that sample average is x bar, whereas population average is mu. We're just creating that notation in this calculus problem. So here is a problem from start to finish using the midpoint rule. Example 5, I'm specifically given the directions, the midpoint rule, where n equals 3, for this question, which is an integral notation. I could have said find M3, but I don't need to if I say midpoint rule and n equals 3. So remembering that for the integral notation, we start at the bottom value in our case of 0, end at the top value in our case of 6. So we're going to integrate over a 6-unit width. And if we want to have 3 rectangles, then each rectangle will need to be of width 2. This is our delta x. As you can see, I started at 0, I ended at 6, and I jumped by 2 to get my column dividers, right? So I've got my graph split into these points, as you can see by my dashed lines over 0, 2, 4, and 6. Now, because it asks for the midpoint rule, I don't want to use 0, 2, 4, or 6. I need to find the midpoints. This one's pretty easy visually, 1, 3, and 5, but mathematically, if I had to find it, I'm going to take my start and ending points of the first column, divide by 2, and get 1 to be the midpoint. The next column, which uses the end of the first column, right? I'm going to add those two numbers, divide by 2, to get 3, which you can see in the middle. And then using the 4 for a second time, you can see that I get this midpoint of 5. So in case your problem's a little more complex. Now don't forget, because it said the integral of x squared, that's my function. So the thing I'm graphing is x squared. And now I need to find the area of each of these rectangles. Now, they're still all going to be width 2. So I went ahead and purple and wrote all those 2's out. But I need the height. So if I am looking at the height when x is 1, it's 1 in this formula. So I squared the 1 to get a height of 1. It's 3 in this formula, so 3 squared is 9. And again, putting 5 into my x squared function, I'm going to get 25. So finding the area of each of the rectangles, they're all above the x-axis, so I don't need to worry about subtracting anything. I'm going to add them up and get 70. Now, keep in mind, we've talked about the midpoint rule. If you look back to the graph, I'm overestimating by taking this slice that I don't want, but I'm underestimating because I'm missing a slice, and we kind of feel the midpoint rule, although not completely balancing out that over and underestimation, is pretty close. Obviously, we'll learn a way later to find out the exact answer, but without rectangles, our goal was to find this curved shaped piece, and we're saying based on 3 rectangles, it's approximately 70 units. And because we're talking area, area is 2-dimensional, so we need this to be squared.